Alright, welcome everyone to the second video on chemical equilibrium. We're going to apply kind of what we've been talking about with chemical equilibrium and these relationships between chemical potentials to ideal gases. Okay. So, right, for an ideal gas, the chemical potential of that gas is related with its chemical potential at 1 bar plus RT times the natural log of its pressure, whatever it might be. Okay. Right, and this is true for any point in the reaction, right? So again, at equilibrium, we know the free energy change for that reaction is equal to 0, okay? Because it's reached equilibrium, okay? Which is, again, assuming constant temperature pressure conditions, right? That free energy change equals 0, so it means entry change at the inverse is equal to 0, which again means you're at equilibrium, right? So again, if I consider that simple reaction AA going to BB, okay? Right, again, that free energy change for the reaction is related with the number of moles of A times chemical potential of A and the number of moles of B times chemical potential of B. Okay. And so, again, that change in free energy for the reaction, right, is related with minus A mu A plus B mu B. Okay. So if we plug in for what the chemical potential of A and the chemical potential of B is here, right, and then rearrange a little bit, right, I have this term here, okay, and then I have this term here, okay. So I just kind of collected the terms on different parts, right. Well, note, okay, that the standard free energy change is related with the differences in these standard chemical potentials. Okay, so again, this is the free energy that we typically talk about is the free energy change under standard conditions, right? 1 bar, 1 molar concentration, things like that, right? So that is our delta G, okay? And so the free energy of a given reaction, right, is related with its standard free energy plus RT times the natural log of the pressure of B divided by the pressure of A raised to their stoichiometric coefficients, B and little b and little a, right? And this is true for any chemical reaction, right? For an ideal gas, right? That the free energy change at any pressures of A and B can be related with the free energy change at standard pressures with this term RT ln PB over PA, right? Raised to their stoichiometric coefficients, okay? Right? So that PB over PA, we're going to call Q the reaction quotient, right? And at equilibrium, we say that Q is equal to K, delta GR is equal to 0, which tells us that the free energy of the standard free energy of the chemical reaction, right, is related with minus RT times the natural log of K, the equilibrium constant, right? And so that's where that relationship between K and delta G comes from, right? And again, all of this stuff comes from the fact that the chemical potential, right, is related with the molar Gibbs free energy, which has a dependence on pressure that's related with RT times the natural log of pressure, right? That all of this, right, that we talked about, you know, almost a month ago potentially, right, with talking about how the free energy changes with pressure, right, is then related with this change in chemical potential with pressure, and how chemical potential depends on pressure is then eventually related with this chemical equilibrium, and that's how we get these equilibrium constants, right? So the equilibrium constant, right, that we derived, right, or that you are given in general chemistry, right, we showed here, right, how you get those and how they end up being this relationship of products over reactants time, you know, raised to their stoichiometric coefficients, right? All that comes from all of this, all these different relationships here, okay? And then again, this relationship between delta G at standard conditions is related with K in that following location. And again, that free energy change is you know, some constant value that we get in tables and things of that nature, okay? And again, K is our equilibrium constant. Now, often, if we're dealing with pressures, we'll call it Kp to indicate we're using partial pressures and not concentrations, okay? And that's often what we use for gases is Kp. Okay? can also talk about Kc, which is the equilibrium constant dependent upon concentrations. Right? We know for gases that the concentration is related to the volume and the number of moles by pressure times divided by RT. Okay, and so in general, right, the partial pressure of A is related with the concentration of A times RT. So you can use that relationship, right, to get the fact that in general Kp equals Kc times RT raised to the change in number of gas molecules, right, between the products minus reactants, right. In this case, the products is 2, reactants is 1, so that would be 1, right. Right, for when we deal with Q and K, right, we never deal with pure solids, pure liquids, or solvents, say in a dilute solution, okay, which we consider solvents basically a pure liquid in a dilute solution anyways, right. And the reason is because, right, the chemical potentials of these things doesn't really depend on their pressures per se, and it's relatively constant, right, because we're not really changing the composition of those things, okay. And so we kind of lump those in with, you know, the standard chemical potentials, right, and things like that, and so yeah, they don't appear in your equilibrium constants, okay. But we include things that are dissolved in liquids, right, in terms of concentrations and things like that, and potentially activities, depending on you know, if you're trying to be very careful and precise, right. In gases, right, you're typically dealing with pressures, okay, but often you can also do concentrations, right, but you have to be careful as whether or not the equilibrium constant is in terms of pressures or concentrations, right, because if it's in terms of concentrations and you try to use pressures, you'd get the wrong answer, right, so you just got to be careful, right, what units you're dealing with for gases based off what equilibrium constant you're dealing with and such, okay. Right, for the relationship between K and delta G, right, technically you need to use pressures in bars every time because, again, delta G naught is defined as 1 bar, 1 molar concentration, right? So the pressure should be in bar, not atmospheres, okay, when using that relationship, okay. Now, the difference between bars and atmospheres is very minimal, so really you'll typically get basically the same answer, but to be precise, to be accurate, you'd want to use bars, not atmospheres, when using that relationship between free energy change of the reaction and the equilibrium constant.